Swayam Prabha. Digital India. Educated India.
Okay, good morning. So this is more of a tutorial sort of a class. What we want to do is we'll take a very simple, one-sided random walk as an example. So the cartoon that you see here, that sort of illustrates the physics of the problem, that you have some sort of a microtubule or a pipe, and the guy who is walking there is basically a protein, kinesin, or one of those motor proteins. And you can say that it walks only in one direction, not both directions, even though it goes in cycles. That's what you see it going back and forth, but actually it just moves forward. And this problem we did in one of the classes. The solution, so what we do here is we set up the Garning equation, master equation, and then when we solve them, we get a Poisson process. So we know the analytical solution for this problem, and with that we can also get mean and standard deviation and all that. Okay, so now in this class what we want to do is sort of look at this problem in different angle. For example, we'll start with the chemical master equation, the differential equation, and then we try to numerically solve it. Okay, because like I said, in many times analytical solution is not solvable, so we need a numerical method. So we'll take this one and do numerically, because we can also compare with analytical solution because it's available. So that's first part of the exercise. And next what we will do is we take the analytical solution, okay, and using that analytical solution for transition probability, we generate many trajectories. Okay, instead of looking at the distribution of the probability distribution, we can actually create the trajectory many times, and then you can also calculate the mean and the standard deviation at any given time. Okay, there are two approaches you can do, and both of these results can be tested analytically, and the codes are shared with you. This is a Python, small Python code is written, and in the second half of the class I think you should do this exercise by yourself, change some parameters, and then we can discuss more if you have any challenges. Okay, so as you can see, okay, so this is the problem, and then if you write the chemical master equation, you will get this dp by dt is equal to some constant a, that is the rate of jump per unit time, and p n minus 1 comma t minus p. So this is a very simple equation. So we can actually apply simple Euler's kind of method to numerically solve. So we approximate this derivative using a difference formula here, the forward difference between time t and t plus delta t, and then you substitute that here. Okay, and then you can get an explicit formula for Pn at t plus delta t, which depends only on P of n comma t. Okay, so we call this an explicit formula. We know every information on the right hand side at time t. Okay, we can use that to update what is the P of n at t plus delta t. So if you want to write a kind of a simulation algorithm, a numerical simulation algorithm, you need initialization. You need to initialize something. So in this case, the parameter a has to be mentioned. It's a numerical value, and you may want to choose a particular time step delta t depending upon how coarse you want to run the simulations. And then this n is what is the total, the length up to which you want to simulate this. This is more like a x position. But here we have to remember that here this spatial coordinate is discretized in some unit step length, and t max is the time, how long you want to run the simulation. So these are the things that you need to specify before you initiate the algorithm. So here what we can do is, so this grid 0, 1 is initialization. Initially the particle is at origin. So the first cell here, the first index here is the time, and the second one is the position. Okay, so the first position at time t equal to 0 is 1, because that's what the delta function is, and then for the rest of them it's all 0. Okay, so that's our initial condition. Then what you do is simply you loop over time. You go to each time, and at each time you go to each of the spatial location, and then you're going to update this okay, and when you come out of that, you would have basically created P of n comma t, okay. At any given time you have all the probabilities at each of those locations, okay. So so I think Ashwin has put up a small Python code here, and if you solve, this is what you will get actually. So time t equal to 0, it's a delta function centered at the origin, and then as a function of time you can see how the distribution evolves, okay. So basically this is a Poisson distribution. When you go to larger and larger value, it looks like a Gaussian, okay, that's what you see here, and this is something you should be able to test in your computer. You could change the several parameters, like I said before, like you can change a values, you can change delta t, or you can change your n values and so on, so okay. So this is something that you should do. And now, and what we can do with this data, once we have this distribution functions, right, you can get mean and standard deviation at any given time. For example, yeah, we use this kind of formula. If you want to get the mean standard deviation, you know P of n comma t at any given time n, and then you can apply these formulas to get all the statistical quantities from those P of n comma t. This is one exercise you should do. The second one is to create the trajectory itself, okay, individual trajectories, and the way you do that is you can look at the analytical solution that we already obtained was a Poisson distribution, and so here we have written for n prime at t prime, given n prime t prime, where the probability will be at n comma t. So that is given by this time difference t by t minus t prime. So you take this as a sort of the transition probability to find where the next position will be. So here I think for simplification we have written delta n as n minus n prime, delta t is t minus t prime, and then the transition probability basically is written in terms of delta t and delta n. So here what we need to do is at every time step delta t, we have to draw a random variable based on this Poisson distribution that tell you the increment in the step length, okay. So Python actually has a inbuilt random number generator that if you specify this a delta t, that parameter, it will give you random number, or you can also create your own Poisson distributed random number by constructing a cumulative distribution function, and then you draw a uniformly distributed random number, and then you see whether the uniformly distributed random number that is generated is less than or equal to the cumulative probability, and then you choose delta n like that, okay. But in this case you see that we are going to use an inbuilt function to generate Poisson random variate for a given a times delta t, okay. So once you do that, you can basically create all these trajectories. So you start at n equal to 0 at time t equal to 0, call a Poisson random number for the next time step delta t, and then you add the delta n, and then you keep doing this. Each curve here is one trajectory, okay, and you can see that how much variation that's happening, because it is a stochastic process, okay. It has a particular probability distribution for each n. So now when you have this bunch of trajectories, you can go to any one time and then you can find the mean and standard deviation, okay. So we are talking about two ideas. One idea is take the chemical master equation, numerically discretize it, you will get the probability distribution function with which you can get the mean and standard deviation. That's one approach, okay. In other approach, we are not really even solving we are not really using the probability distribution directly, but we generate the trajectory based on the probability distribution itself, the transition probability, okay. So both approach will become very handy going forward depending upon the complexity of the problem. And as I said before, for this problem we know the analytical solutions for the mean and standard deviation already, okay, and then you should be able to compare all the three things. So here I think we are comparing the numerical, simulation and theoretical. Numerical is the Euler's method, simulation is the trajectory that we have created, and theoretical value we already know, okay. And you can see that mean and everything is nicely scales with the time t, okay. And so here the variance is plotted as a function of time t, where you see that numerical and theoreticals are exactly matching, but the simulation trajectory is almost same, but you see some deviation. This is mainly because the standard deviation also grows in time. So you need more trajectory to average when you go to larger and larger times. Here I think we created some 50 plus trajectories. Let me see how many trajectories we have created. Yeah, he has made 500 trajectories, okay, but if you make it 1000 and more, you will see that even this one will also be matching, okay, or vice versa. Instead of 500, if you do just 10 trajectory, you will see that your prediction is going to be far more off from the theoretical value, okay. So with this introduction, I think Ashwin has already shared the code with you guys. Please run it and try to use all these two approaches, and then ask me if you have any questions. Okay, please proceed.